still says, oh, there we go. It just changed from off air to live on my end.
Yep. Well, now, while we're waiting for other folks to join us, why don't you tell me what you've been doing with Tiltmeters?
So last time we did this, which was a while back, I was talking about these Tiltmeters from Joule Instruments that are super precise, 1 microradian resolution, and sending them to Antarctica.
Yep.
So I've got the loggers done. They're shipped off. They're going to be going to Antarctica probably in less than a month. That's all great. But now they're excited about some of this and want to put them out for a couple of years. And power is an issue because these Tiltmeters are always on, and they're not exactly power efficient. So it's an issue when you have no sunlight for 6 months.
I could imagine. By the way, Vic says he's going to be a couple of minutes late, but he'll be in shortly.
All right. And well, so the solution for like seismometers has been, there's these giant things, UNAVCO is the company that does them, battery packs, where they literally fly in a pallet, about 1,000 pounds of batteries and huge solar panels to get the seismometers over the winter.
You know, there's something that's occurring to me about overwintering stuff in Antarctica. And it's a bit of a thermodynamic trick.
What are you thinking?
Pelletiers. Because of the fact that the ice itself is going to be warmer than the air around it if you go down a little ways, and you can get a large enough thermal gradient, then that means that you're going to get rime ice forming on whatever you have penetrating into the ice, and at the same time, you're going to be sinking the temperature from the air, which is significantly colder, into that rime ice. And the thermal gradient that you get is going to probably be about 20 degrees C, which is more than enough with a step up to generate some power. The reason I'm thinking about Pelletiers in Antarctica is because this new project that I'm going to be working on soon at UMN involves putting a Pelletier device on the back of a penguin as part of a tag.
Okay.
It's something that I've been talking about with Michelle Leroux out at UMN. We're looking at doing a tracking SATCOM tag for a penguin. But the thing is, emperor penguins, when they get into a huddle, can bring the center of the huddle temperature up to about 70 degrees Fahrenheit, while all around them is like -40. So these birds are leaking heat like you wouldn't believe. So you put a Peltier on the back of one of the birds, and it happens to be on the outside part of the huddle, you have no problem generating watts of power.
I was just going to ask how much, because I know we're talking probably for some of these instruments, several watts. So that's interesting.
If nothing else, you might be able to do one of those situations where, yes, you're going to have the batteries discharging fully by the end of your deployment, but you can delay the discharge by doing a cyclic recharge over whatever period, or in your case, aperiodic set of time you have where the temperature is higher or lower. Hey, Vic.
Hey, guys. What's up?
We're talking about Peltier devices in Antarctica.
To make things hotter?
No. To harvest energy.
Oh, interesting. Well, what are you going to use for the hot side?
The ground.
Okay. I've had some.
It's only funny because it's true.
Yeah, I guess so. I tried to actually use a Peltier to cool down like a small chamber, but I got one of the cheap ones from eBay. I think you really have to get some kind of good quality ones for them to be effective.
How many degrees was your differential?
Well, it was room temperature outside, and it was like probably it was like 10 degrees probably hotter inside Celsius.
That's not good. I've got a few that I've been playing around with down here. If you want one, they're the like 2-inch square ones, and I've been able to get like 40 degrees C easy on those. I mean, like hot enough to burn you on one side.
Yeah, for sure. I mean, did you get air? Were you just cooling air though?
I was. Let's see. One side was attached to a piece of plastic that was at room temperature with cyanoacrylate, and then the other side was just loose in air with no heat sink.
So, what side was loose in air?
Hot side was loose in air.
Hot side loose in air. And you had 2 big old fans on either side of it?
Nothing.
Really?
Yep. 30
so
to 40 degrees C.
You were getting it to cool the air.
No, I was cooling the
versus
plastic,
outside?
heating the air.
Heating the air.
Yep. And it
I
worked
wonder-
because there's enough thermal mass in the plastic.
Yeah, that's probably it. Because I was actually just trying to move heat through, air inside to air outside. I was just trying to cool the air inside. I don't know. I'm not good at whatever you call that. What is it, like thermodynamics?
Yes, that's the exact word. In a word, yes.
Yeah, I don't speak BTUs.
Good. Neither do
nobody
I.
should
speak
speak
joules.
BTUs.
Yeah.
Joules, yeah.
Delta K, delta degrees C, and
Yes. Right, that's right.
and
I think-
delta
isn't it
K
like
for
specific
or
heat.
joules.
That's a thing, right?
yes.
the
Thermal
whole
mass as
MCP
well.
delta T thing.
Yeah, CP.
Yeah.
It's like Q equals CPM delta T, right? That's right.
Yeah. Yeah.
Yes. Not to mention
I think I did a
Pivnert
science-
as well when you're dealing with gas.
What was that?
I said not to mention Pivnert when you're dealing with gases.
Oh, yeah, true.
Ideal gas law, thermal transfer. It works.
Yeah, meteorology, we have a little bit of that.
A little.
Sure.
Well, no, you don't. You don't have ideal gases in meteorology.
Oh.
Hey, our first assumption is ideal gas.
And spherical cows in an infinite frictionless plane.
Well, what do you want? Good weather forecasts? I mean, come on.
I guess those would
Well-
make life less interesting, wouldn't they?
The atmosphere is not compressible? Is that the problem?
Now you're in water. Now
Ah.
you're where I used to be.
Yep.
But so,
Fluid dynamics.
Vic, actually, just before you got on, we were talking about so the tiltmeter things with your Wildfire boards are done and working great and off to Antarctica.
That's awesome.
NASA came down and picked them up about 2 weeks ago.
Uh-huh.
They've been playing with them, and they're out of here. And
Cool.
so I've been talking about, I think I'm actually going to start manufacturing my own tiltmeters.
Uh-huh.
Buy the sensors. You can get 1 microradian sensors for a few $100 per axis. But the ones that I've been using that are, all made in this nice little case with leveling feet and all that, they're $5,000 for the instrument. And as we saw, the instrument is really awful in this bad asynchronous serial
Oh, yeah.
firmware buggy mess. So thinking about buying the sensors and then rolling my own instrument on top of them.
That sounds cool.
Because what they're thinking about now is another group has seen this and said, oh, we want to put them out, but for years. And they have to survive 6 months with no sunlight power-wise, which these
Right.
never do because they're pulling 80 milliamps.
Mm.
So we need to be able to turn them off and on and really squeeze down on power.
Right. That's pretty cool. That's a really, so turn them off and on. How much, you say they draw 80 milliamps?
Well, the whole setup that I'm sending to Antarctica right now, so logger, GPS, tiltmeter, all that together draws 80 milliamps. But over the winter, really, all we need them to do is turn on once every 5 minutes, log the time, take a tilt measurement, turn off, and then once a day, sync up a real-time clock to GPS so we don't drift.
Got it.
Instead of having the GPS on all the time and using the pulse per second to trigger taking readings and all that, it's
Right.
fine for short field campaigns, but awful for going over the winter.
Yeah. And is it like, I always forget, like winter is nighttime all the time then?
Yeah, so
Local
our summer,
winter.
their winter's nighttime.
Yeah, okay.
So right now it's starting to get more and more light. People are starting to trickle into McMurdo slowly. And in November, things will really ramp up, and then the field season will end in late January, February sometime. They'll start flying people and equipment back, and then the winter over people will go crazy for the next 6 months.
Cool.
Wasn't there a book that was recently released about that?
I don't know about a book. There's an excellent documentary on Netflix. A guy that wintered over and his hobby was photography, did stunning time lapse of like stars and all kinds of stuff over there.
Nice.
And he built all of his own little setups.
That's cool.
Yeah, it's neat to watch. So, Vic, are you going to Open Hardware Summit this year?
I have been saying I'm going to go, but I haven't got tickets yet.
Okay.
So I want to go, yeah. But it's like the 8th, right? The 8th of September, something like that?
19th.
19th? Oh, better. So it's the week before Maker Faire. 19th. Yeah, I mean, I think I probably will go. It's only like 3 hours from Ithaca to drive.
To Philly?
Yeah.
Well, then
Really?
again, you're
3.5
by the airport.
hours probably is more like it, but
Okay.
Wait a minute,
it's not
to
that
Philly?
far. Yeah. Philadelphia's
Philly
like
from
3.5
here is
hours away.
4.5 hours minimum.
No. I don't
Okay,
think
maybe
so.
you just drive faster than I do.
can drive. Well, that's probably true.
Also, the other thing is that Philly is a 1-hour flight away from Ithaca, and
That's true,
Vic
too.
happens to work right next to the airport, and it's
Oh, cool.
what, like $200 from Ithaca, I think.
Yeah, it's probably
So-
it's direct, so it's probably not
Yep.
a big deal.
Oh, wow.
And you can expense it, right? I mean, you're made of money
Yeah.
over there at Wicked
Oh,
Device.
actually, it's an interesting view on the world.
I know. I'm sorry.
Yeah.
I shouldn't joke about that.
Do you know how much particulate sensors cost? They're not cheap.
Too much.
Yeah, too much for sure. So yeah, I'm planning to go. Are you gonna be
Okay.
there, John?
I'll be there. Yeah.
How about you, P? You gonna make the trip?
Unfortunately, I can't. I had something else that I had forgotten about before I registered to give a talk, and then they didn't get back to me in time, so committed to the other thing and had to email them and tell them no can do.
Oh, that stinks.
I see you're representing Ithaca Generator. Very nice.
Oh yeah.
But
Got the
John
rocket
was
ship
actually
there.
just telling me that they had my talk up on the site already, even though they hadn't gotten
Oh, they
back to
did?
me. Yeah, and it was going to be calibration in citizen and community science.
Oh, interesting.
So
I've been dealing with a lot of that lately. I bought a let's see, one of these things. You recognize that, Pete? That's a temperature probe in a green liquid.
why is the liquid green? Oh wait, let me guess. The temperature probe is corroding.
I think it's probably actually just some kind of a thermal insulating fluid so that it gives you more stable readings or something like that.
Just a thermal fluid, and it doesn't freeze like water.
Right, it doesn't freeze. But,
Do I hear
you know,
Dirk
I'm
in the
measuring
background there?
Yeah, Dirk was explaining how it works.
You should tell Dirk to call in.
Dirk to call in? You got an invite, right, to the instrumentation time?
I thought he did.
Oh, he said he didn't get invited, so it's your
Well,
fault.
that's my fault then.
But yeah.
I'm
so
sorry.
I got this. We got this thing from Thomas Scientific, which was a bit of a, it was a bit of a circus act in itself because I had to get it shipped and they didn't ship it, and then 2 days later I found out they didn't ship it, and then they overnighted it and it didn't get here Saturday. Whatever. I got it finally, and I wrote a Node.js application to basically read the data from like 10 connected serial ports, and I punch in what the current temperature is and the current humidity, and it puts in like the unique offsets for each device, so that they, that really sensitive SHT-25 we were talking about way back when.
Yeah.
They still have quite a bit of variation among them, despite their purported 0.2% accuracy in temperature.
So did they misspell it? Is there supposed to be an I in there?
Perhaps. But
Hi,
actually,
Don, by the way.
they're really nice sensors. It's just that we're taking another step just to make sure that, I guess, to account for variations due to enclosures and whatever else, I guess, adds up. So yeah, been doing mass temperature calibration of air quality eggs.
Well, speaking of actual calibration, it's looking like we at the Soil and Water Lab down here on campus will probably be actually building our own cal lab sometime very soon, within the next couple of months. And the first two acquisitions are going to be a highly accurate thermistor thermometer and and a volt/amp source meter. So by having both of those, we can pretty much throw in whatever variable DUT we want and come out with a traceable calibration that if we get funding from the Atkinson Center here on campus, we'll actually be accredited by A2LA, which means we can give you an accredited calibration certificate and say, here you go, you're ISO 17025 compliant, or ISO 9001, or pick your flavor of ISO.
Right.
And yeah. By the way,
Cool.
John, it was Big Dead Place that I was thinking of. The article is there in the chat window. It's being developed by James Gandolfini of certain New Jersey mob series fame into a series on HBO. It's basically about what actually happens in Antarctica during overwintering and how people pair up with ice wives and ice husbands amongst themselves and all of the social dynamics.
Yeah, even
Apparently
not
guy-
overwintering, the dynamics are pretty weird.
Yeah, apparently the guy who wrote it has been uninvited by Raytheon from ever going back to McMurdo. So,
Interesting.
yeah, apparently Raytheon runs McMurdo for NSF. I didn't know that.
Yeah, and McMurdo's going to get totally torn down and rebuilt very soon. They've got a huge, huge amount of money set aside, and it's going to be really nice. Instead of a bunch of different outbuildings, it's going to be all connected, and like you can go in, take your shoes off, and not leave until you need to go outside to go between living quarters, slabs, calf, all that. It's going to be nice.
Sounds a little bit like the University of Minnesota campus. They've got these walkways in between all the buildings, both above ground and below ground, so that in the winter you don't have to go outside.
Nice.
So, by the way, introduction here. John Lehman and Victor Aprea. This is Don Blair, whose audio I hope is working this time.
Can you hear me?
I can hear you.
Oh, good. Okay, very good. Hello.
Hi.
I'm Don.
Hi.
I didn't know what to expect, and it was wonderful to come into the conversation and just see people holding random instrumentation up to the webcams. That's very exciting.
I have an iPhone.
Okay.
That work? Oh, and here's a writing implement.
Cool. Nice. Good. Great. Cool. Yeah.
So the three of us kind of know each other already, but Don, why don't you introduce what you do and who you're with?
Sure. So I have been working with this nonprofit Public Lab, and there I'll type in publiclab.org, and they're focused on making open source instrumentation for environmental monitoring and trying to make devices that are as accessible as possible for folks to use. And I've been focusing on water monitoring, and I don't know a lot about it, but I've been starting to make a kind of Arduino compatible board for use in data logging and being used outside. So I've been playing with that. I recently got back from Colombia, where a bunch of people there were interested in these devices or taking that kind of approach. So it's been really exciting to connect with Pete about the stuff that he's doing. And one of the biggest issues, actually, in the stuff that I've been working on in this kind of environmental nonprofit, where they have a lot of folks that are interested in advocacy and environmental monitoring and trying to use data for advocacy, is trying to collect data that is considered legitimate by the various audiences that these advocates want to interact with. And so these conversations around calibration are really exciting. The idea that we could make these cheap instruments and then get them sort of blessed by a process such that other people would kind of consider the data to be useful. So
Touched by the calibration fairy.
Bing! By the calibration fairy. Okay, that's great. Okay, good. Which you will. So you dress up.
Great, I'm the calibration.
You are the calibration
I don't want to be the
fairy.
calibration fairy. We need a T-shirt now. I don't want to be the calibration fairy.
Oh, no, you don't. It's just a tiara. I think you don't even have to wear the whole.
Well, he needs a wand for sure.
Yeah, a wand.
Yeah, I can't just poke it with my finger. There you go. You're done.
I mean, as far as my understanding goes, it might as well be waving a wand over it, because I'm sort of new to all this, so I'm excited to learn more.
Well,
and
In the
Yeah.
calibration industry, there used to be a term that then took too much of a negative connotation, which was lick and stick, meaning that the stickers used to be lick and push type of stickers that you put over the screw holes after you were done with the calibration to make certain that somebody didn't modify the instrument.
Oh.
And so since they went away from the lickable type of sticker and away from the term which had more than a couple of double entendres made about it, it instead turned into peel and seal. But either way, if you just have a peel and seal operation, that's still not a good thing.
Peel and seal.
Yep.
Okay, kind
Because
of
you peel the sticker off and then you seal it over a screw hole. There are specific kinds of stickers that are made to specifically fragment into millions of tiny pieces when you even touch them with a screwdriver or a razor blade or what have you. I know about this from personal experience, of course. So
I'm trying hard, and maybe it's with the wand. It's guess and bless. I don't know. I have no idea.
Wow, I like that one.
Guess and bless.
Guess and bless. I can get on board with that.
Yeah,
well,
actually, I don't know.
You just get like a high council of elders to everything.
The Fellowship of the Cow.
Yeah.
So actually, Don, you'd be very interested in both some of the environmental sensing, especially on the tilting side of things that John's been doing, and also on the meteorological side. And Vic is one of the two owners. And how would you classify yourself within Wicked Device? You're the chief engineer, or what?
Do all the development, so all the like hardware and firmware
You're the
development.
CTO, right? Essentially.
Yeah, that's probably it. Yeah, we're not a corporation; we're an LLC. But so
you can still be the
yeah,
CTO within an LLC.
Sure, I'm the CTO. Fine.
Cool.
So he's the guy who's responsible for the Wildfire board that we used at the stream gauging workshop, and
Very
the
cool.
first person I know of who's managed to put an RFP, what was that, 69 or whatever series that was, 433 megahertz.
69?
Yeah.
Yeah.
RFMs. Yeah. Anyway, one of those 433 megahertz modules, a micro SD card, and a CC3000 module all on the same board, and get them to play nice together with an Atmega.
Beautiful.
Yeah.
So
Yeah, it's a nice board. I like it. I think.
You would.
Well, yeah, I spent a lot of time making it, so I like it. Don, I've heard of Public Lab actually. They're based in New York City, right?
Yeah, they've I mean, they started in New Orleans, and then they've got someone who's based in New York, and then there are a bunch of us in Boston, and then there's folks out in Portland. But yeah, they've done a bunch of stuff in New York. Oh, that's exciting that you've heard of them.
Yeah, I think I met Liz Berry, and I can't remember the other girl's name that we met, but we went. I mean,
was it Gretchen?
Shannon. I want to say Shannon, but I don't remember.
Shannon. Yep. That makes total sense. Yep. Liz is based in New York, and then Shannon often goes through New York. Yep. When was that? Was that a couple years ago?
Yeah, we went to EcoHack.
Yeah. Okay.
2012 or something like that.
Okay.
And that was like right before.
Oh, that was air quality stuff, was it?
Yeah. So we make the air quality egg as a
right.
product.
Okay. Cool.
Here, I've got one here.
See, you've got show and tell. Good job.
Nice.
Yeah.
Very cool.
I've been calibrating them right now, so.
Great. I would love to hear. I mean, at some point, I'd love to hear about across. Public Lab has got this project in Wisconsin now where they're trying to do air monitoring because of some silica particles that get put in these mining processes, and there are all these issues around calibrating into. So it'd be neat to have you in on those conversations.
Yeah, I could definitely. I'd like to. Yeah, definitely get connected. That sounds cool.
And besides, particulate is definitely something that you guys are into monitoring.
Yeah, we're coming out with a particle sensor in the next month or two here. based on the Shinye PPD60PV, if you've heard of that.
That's a lot of P's.
I've heard of I've heard of a Shinye, but I don't know which is which.
Yeah. So we were using a Shinye before. So we were kind of like transitioning from our version 1 technology to our version 2 technology.
Okay.
And we were using the less expensive Shinye sensor originally, and we're going forward with their sort of next tier up particle sensor. So
Thanks, John.
Cool.
Yeah.
Oh yeah, it is the PPD60PV _E.
Yeah, I had to type it real quick
T2,
before I forgot all the letters.
Actually. I think there's like a T2 at the end of it.
Is there? Okay. Oh, thank you. Okay, cool. Oh, that'll be really fun to check out. That'll be great.
Yeah.
Good grief. This thing's just what, a phototransistor and an LED with a bit of optics in between, isn't it?
I mean, it's a scattering mechanism that it works based on, but it actually has an analog output. So they've got some amount of processing, like signal processing going on board.
So then you could. How much are these per?
So like if you go to buy them online one at a time, they're like $295 each.
What? Okay,
Yeah.
the reason why I'm asking is because it looks as though it's an indirect path with a mirror in the middle. In fact, I think I've seen a teardown of one of these once, or something like it. Or maybe you just have one part in the lab.
They have like a resistive heating element in the base of them, so that they create a
convective current.
Convective current airflow to get particles into the chamber and then up through the chamber and out the vents on the top. And I think there's a fair amount of like mechanical sophistication to them.
Okay, the reason why I was asking was because I was wondering if one of those sharp short-range distance sensors and a large resistor and a small mirror could be used to affect the same exact thing.
Well,
although that would have to be in the IR.
That's sort of general, right? Like when people talk about particulate matter as a sort of a health effect, they're usually talking about very kind of specific particle sizes. Sort of like PM 2.5 and PM 10. These things I think are somewhat tuned to pick up particles that are in those like micron ranges, 2.5 micron and 10 micron, and so do it yourself is possible for sure. But I think where they have their value proposition is in some effect of how they've sort of at the hardware level been able to discriminate particles at that size and composition.
It says half micron up.
Yeah, so the actual thing
impressive.
does. Yeah, it can actually detect particles that are half a micron and bigger, which is pretty cool.
Oh man!
They also
I
have,
wonder
there's
if
other
they're
ones
doing
that are
it
out
by
there.
what wavelength they're using.
Yeah, could be infrared based. I think it's infrared, but I don't know exactly which wavelength it is.
Because half micron is going to be 500 nanometers, which is going to be yellow-green. No, mainly green.
Is it really?
Yeah.
Huh.
550 is green, so...
Yeah, it's laser pointer green.
Right?
Yeah.
One of the... Oh, sorry, go ahead.
No, so, yeah, if you've got between IR and 550, then you can get down to half micron, but if you're basically going by what wavelength can be scattered, then you essentially are considering the lambda over 2 is going to be equal to the diameter of the particle.
Right.
So
something like that.
if
I'd have
actually,
to
if it's going to be a lambda over 2, then that should theoretically go into the UV. If it's going for half micron, it might just be 1 lambda for straight scattering.
What John said, I don't know if you're being, you said laser pointer. I think that's the problem with like LED light, right? Is that it's not very coherent.
Right.
Mm-hmm.
But they do have laser-based particle sensors out there too. It's just, I guess I'm not sure what the actual mechanics of this one are. I haven't really spent a lot of time with it yet.
Yeah, I mean, that's how we had some sensors for meteorological measurement stuff that were laser-based that you would actually like put on a wing and fly through clouds and get
Cool.
particle shapes, particle size distributions, all that stuff. It was basically a red laser beam line going across,
Right.
because that's
That's cool.
the size they cared about. And at AGU, actually, every year, the company that makes the one, I can't think of the name right now because it's been years since we messed with it, they have a humidifier blowing up, their own little cloud, and you can watch in real time all the different sizes and distributions go by. It's a pretty neat instrument, but it was tens of thousands of dollars an airplane, so that adds, factor of 5.
A lot to it.
Yep.
Yeah, that way, and in terms of calibration, it would be the humidifier sounds like a kind of cool way to do it. Like some setup where you could assess how well it's working, because that was one of the things that has come up, like how good are these sensors, and what are the vague impression that I get is that some of these detectors are kind of intended for like industrial applications where you're worried about really high levels of particles in the air, and so it would register kind of like above a really high level, and that's all you want is like a threshold, like everybody get out of the building.
Right.
But then
that's
Turn the fan on.
Yeah,
yeah.
That's interesting. That's like that's kind of what we came from in an evolutionary standpoint. We were using these sensors that were used in automotive industry originally for our nitrogen dioxide and carbon monoxide sensors.
Uh-huh.
And so they were, their mass market uses is threshold detection really. And we were kind of assessing with our like version 1 hardware whether they could suitably and accurately measure, use as measurement devices.
Right.
And I think we basically kind of came to the conclusion ultimately that, they give you some information, trends more than anything else. But when people have an expectation that the concentrations that you interpret are sort of accurate, not just from a relative standpoint, it totally changes things. So what we've actually moved on to with version 2 are electrochemical sensors. So they actually have NIST-traceable calibrations going on with them too. So.
Oh wow. Okay. Cool.
Yeah.
Yeah. No,
it's always interesting though. Like when you talk, Pete, about like, I think the first thing you always kind of jump to is like, oh, you can do that by doing this, and that. Like,
But then again, I'm also assuming that I can calibrate the sensor afterwards with NIST traceable standards. So.
Right. Yeah, all you need is like $100,000 lab, and then you can do anything.
Maybe about $10K. Why not?
Oh yeah.
But on our side in the soil and water lab right now, we're running into the same sort of thing for nephelometry, which is the in-water version of what you're doing. And what we're doing is, for turbidity sensing, we're just taking a white LED and a photoresistor, and yes, the response curve is completely different from one pair to another. But by calibrating each one of them, we can still keep the price down and the equipment cost low. And luckily, I mean, for turbidity at least, the overall kit for actually doing the standardization and everything is only running us about $600. So that's a little bit better. But apparently there's a lot that...
Can you actually buy commercial stuff for that? Like, is there OEM sensors for what you kind of built from scratch?
Unfortunately, the only place I've seen the sensors for that is in situ in the instruments themselves to measure it.
Yeah.
Okay.
So, nephelometry is kind of like, well, the state of the art in nephelometry is still the Secchi disc. So, I mean, that tells you where we are right now.
What kind of discs?
It's essentially a little disc. It looks like the BMW logo in black and white, just like you'd see on a crash test dummy. It's essentially just 4 corners of black and white on a disc. You put it in the water to some particular depth, and you basically judge how well you can discriminate the borders between the black and the white parts. And you rotate it, you do it again, or you do it at a different depth, and that supposedly gives you in NTUs, which are nephelometric turbidity units, how cloudy the water is. But the thing is that that's essentially a psychosubjective measurement. So some people, like the EPA, have gone on to NTU measurement by way of actually doing an optical path loss method, and that's what I'm trying to duplicate. So once again, like you said, I'm going for the cheaper route, but I'm also working on it from the perspective that I have this expensive thing that can guess and bless, as we were saying before, and say the sensor is definitely so many volts per NTU. And then if I put that into an Arduino, then it's so many LSB per NTU in the sensitivity.
Yep.
But that's kind of the direct linear method that I'm using. And I do wonder if you couldn't do the same thing in air, although I don't know how well nephelometry would transfer to air. I mean, after all, if you've got enough air that a Secchi disk could, if you've got enough particulate matter in the air that a Secchi disk would work, you've got bigger problems. You don't want to be breathing that. You're in Beijing on a bad day.
Yeah, you might be in Beijing, I was going to say, exactly.
Yeah.
Or Los Angeles in the mid-1980s. Same thing, really.
Kind of, yeah.
Don, you freeze-framed looking extremely happy there on mine.
Considered evidence of air pollution if it just looks really hazy.
Oh, jeez, okay.
So in a way, that's almost like, like, can I see that building over there? It's almost like a Secchi disk approach, I guess, in there.
Oh, yeah.
Well, I mean, especially with the straight lines and nice big windows that you guys have on the MIT campus.
Oh, I just heard about this artist. Well, there's this artist at Northeastern who's arranged in some cities to get permission for a big building to control the lights on in the building at night, and like make patterns. Like we should do this. That would be amazing. Like we could get like a big building and make a grid pattern and then just like
put a camera in every window and one facing it.
Yeah, exactly. Yeah, that'd be good.
The only problem is we gotta make certain that the cameras don't re-white balance themselves, because then all of your measurements just go.
Oh.
Which I don't know about you guys, but my laptop camera keeps white balancing every moment that I move myself. I'm like over here and it's re-white balancing versus this. Screw it.
It's funny because that's another thing. Like in public lab, one of the things that people got excited about was using smartphone cameras for spectroscopy and other things. Mm-hmm. But that turns out to be one of the big sticking points that you just have very little idea. Even the manufacturers can't always tell you what the camera is doing and what the specs are, because they'll just swap it out with the cheapest thing, or there's some new thing and they just put it into their manufacturing process, and there's all of this like black magic that goes into the white balance, so to speak. Yeah.
Black magic and white balance. I like that.
But yeah, I mean, like you just, and there's like there are these Bayes filters that they use that are these films that are on top of the. It's all this magical stuff, and it's really hard to calibrate that stuff. So I've been to kind of move towards essentially making their own detectors with the sort of thing that Pete is talking about, like just a photoresistor and maybe a filter in front of it, and so that you're getting only certain wavelengths, and there's no magical thing. It's just a voltage or whatever that you're measuring.
So all three of you guys now are saying like John's making his own, John's making his own tiltmeters. Pete's making his own water meters.
Nephelometers.
Nephelometers. Water meters. I mean,
what a name, right?
Yeah.
Nephelometers. That's just a mouthful.
Yeah. Rather.
But anyway, yeah, like
very dirty water.
Kind of interesting though that like that's where things kind of end up going, is like the what's available just doesn't cut it, or like or do we all have like some kind of neurosis that's like gotta make our own or else it doesn't matter.
Well, I mean, part of it for me, especially with the tiltmeters, is I could probably mess with it or work with the manufacturer a little bit to get exactly what I need. But when you email the manufacturer and say, you have a firmware bug that when I put it into this mode, things go bad, and they say, thanks for letting us know, we're not going to bother fixing it because this is a low volume product. I have no faith in their
the commitment.
Ready to get away from it.
Have control
when they don't even bother, they get bought by another company, and then like parts of their output say one company name, parts say the other. They send you manuals from one company with a unit labeled for another, and the engineers didn't all transfer over. It's just a nightmare, so we're ready to get away from that.
That's cool.
And on my end, I mean, you take a look at like what Onset's doing with data loggers for pressure-based depth sensing, and it's like, what the heck are you guys doing? You don't account for the fact that there's all this salinity change. How can you get depth from pressure when you're getting like a 2.5 to 5% change in your density over just the course of a day? And so first of all, the technologies that are out there that are cheap enough to use, like the Hobo data loggers, aren't actually good enough or precise enough for what we need. Then you got the other end of the spectrum, like ISCO, and there's some Teledyne brand that's now making the bubbler pressure sensors for the USGS, and those things are $15,000 a pop, plus $10,000 to install, plus $10,000 a year to maintain. And you look at that versus making your own multi-parameter stuff. I mean, for my conductivity sensor, I use two 0.1-inch female headers with 0.9 millimeter pencil leads rammed into them. If I cut them off and then I calibrate it, I've got a conductivity sensor. It works. So the question is,
what about like all the what's the word for them, like second order effects? You know what I mean? Like, what about temperature and all that kind of stuff?
It's a good question, and that's why when I do the calibration, I do it at more than 1 point of temperature.
So do you make like a multivariate model to interpret your raw values from?
That's what I do first, and then if it looks as though it's flat enough in one of those dimensions, then I essentially throw that one out. So, like for example, if conductivity.
So what is the technique? So maybe that's something you could talk a little bit about. Like, what's the technique you use for coming up with a multivariate model? Do you start with first principles? Do you just like throw it into a linear something program and out pops a model, or what? You know.
First of all, the first thing that I do is I just graph it. I don't care if I'm using Excel or R or what have you. I do a straight calibration at room temperature, with the x-axis being the independent variable that I'm measuring and the y-axis being number of LSBs that I'm getting back on my ADC, whatever it happens.
Yeah, your raw measurement.
Yep. So that's the other thing, is that, yes, I usually do these using something like an Arduino, which means that I do have the Arduino's own transfer function that I have to worry about later.
Right. But
the thing is, that's something that I'm going to be doing something about anyway. That's a calibration or a characterization that needs to be done anyhow. Anytime that you use an ADC, I don't care who you are, what you're doing, you need to test that at multiple different temperatures, at multiple different voltages for each one of the ADC inputs, because otherwise you don't have a proper mapping of the transfer function of voltage in versus LSBs out.
Right.
So then, assuming that I've already...
I'll just say quickly, that's amazing. You know, just amazing to think like how many people do not do that.
Pretty much like, everybody doesn't do that. I'm someone who does.
Is that?
It's hard, right? That's why.
Is that a big effect?
Oh,
like temperature on the ADC?
Yeah. Well, actually, the thing is that
it depends on the ADC.
Reference voltage, because of the fact that you've got band gap-based reference voltage, and the band gap itself changes as a function of the thermal noise. Basically, the Johnson-Nyquist noise defines the actual band gap in the band gap reference. So if you're at negative 20 C, you're going to have a much lower threshold voltage that your electrons are jumping over within the band gap reference than if you're at 20 degrees C. So within that 40-degree range that I often see things being measured in, and obviously considerably higher, we get up to about 40 degrees C on a regular basis if you've got something that's sitting in the sun in a box. So within that 60-degree range, there's a lot.
I think it matters. it matters what I think it matters what ADC you're talking about, though.
Well, if you're talking about the on-chip one for a microcontroller, then
Yeah.
it's not going to be designed specifically to
No,
do
that's
large ranges.
right. That's true. That's true. The embedded ADCs are not like great for that. But like if you use an external ADC, they can be spec much better, right?
That's true.
That's like point something % per degree.
Yeah. So the one I'm using on air quality like is an 18-bit ADC from Microchip, and its specs as 50 nanovolts per degree Celsius is its drift.
That's really good.
I mean, yeah, and it's
probably only cents per part, right?
It's like $1.20 or something like that per part. But yeah, it's pretty.
The thing is that by comparison to just having one microcontroller board rather than having to like push shield on with an ADC or anything like that, that's why being able to do the math post hoc in post processing, so to speak, becomes appealing.
I guess in some sense, what you're saying is you can spend a lot of energy to save a lot of money.
Exactly. Yeah, especially in academia, that's how it often goes. I mean, John, I'm guessing you've seen this too, where you can spend loads of time repairing something, but you can't spend 1 red cent on actually getting something better, which kind of sounds like your Biax machine, doesn't it?
Yeah, a little bit. I mean, I try to ride the middle of that line a little bit more. I don't try to build everything. Like for these tilt things, I'm going to buy the sensors and build the platform and build the logging side of it. I kind of adopt that in our lab too. A lot of times in the past, people have built load cells to save money. Like they've had beryllium copper turned and glued their own strain gauges on it and all this stuff. I'll buy the load cell and calibrate it with my NIST proving ring. Granted, I've spent $800 on it instead of $200 in machining costs. But to me, there's a line to ride between the time.
Yeah. It's interesting.
I definitely agree because, I mean, like with the depth sensors that I'm using that sharp distance sensor rather than using just an infrared LED and photodiode on my own. I definitely agree that there's definitely a place for doing that with buying the sensor whole.
Yeah.
But to actually save on the input cost in parts, I'm perfectly willing to build my own sensor if need be, because, like I said, with the nephelometry stuff, there's just nothing out there right now. And for the conductivity stuff, it's essentially just 2 electrodes in water anyway. So for both of those, the sensor design and build is really simple. But when you get into like high precision temperature sensors, I'll buy that. If you're dealing with a depth sensor, I'll buy that. I mean, for what I'm doing, an LM50 works fine.
It's interesting how there's like this whole spectrum of possibility where you can.
Yeah, definitely.
Yeah, and it'd be nice, like for folks that are coming into these things, it'd be really nice to have like just a little characterization for like just like Pete said, for temperature. You probably want to buy the device. You probably don't want to worry about all of these issues. For conductivity, even with the fancy probe,
it's still just 2 pieces of stainless steel.
You don't want to calibrate them anyway. So if you make your own, the process that you go through to kind of check to see how yours works and characterizing it is not so different from the process of calibrating it after it's been in the field. So maybe it's not a big deal, but I agree. It's like it's neat to think about how to approach each of these problems, because it does seem like there's not one answer.
And there's also the fact that you can do post-hoc or pre-hoc. I mean, you can do pre-cal or post-cal on any of these things. So if you need to get this thing built and get it right out the door, you don't necessarily have to worry first and foremost about doing the ADC cal, for example. But that being said, you're also not accounting for any aging drift, which that's a whole nother conversation.
That's interesting. The whole what do you actually log too when you're doing logging? Do you actually try and do interpretations in hardware, or do you just log your ADCs and hit it with Python or Excel after the fact? I don't have that luxury because people don't care about volts, right?
I always just pull it in LSVs and then I'll do a post-hoc post-processing based on whatever the characterization of the transfer function is that I get.
Yeah.
Because essentially that is what amounts to my sensitivity. My sensitivity is actually multiple transfer multiple transfer functions multiplied by one another. Because it's going to be the volts per LSB transfer function, which is essentially a sensitivity in its own right, and then it's going to be the volts per, or the units per volt in the sensor itself. And then
plus there's an offset too.
Pardon?
You're right, every sensor might have a different offset too.
Exactly, and not only is there a different offset and a different sensitivity, but there's also going to be different temperature dependence, and there may even be a different aging factor, which goes back to what I was saying before about ideally you want to get before, maybe even during and after, but if you have a different aging function, like actually John, I think you had observed this with that that gravimeter that you had made, the capacitive one made of conductive foam.
Yeah, actually, before we get off the call, I want to update on that.
Oh yeah, let's.
But
Segue.
Go ahead with what you were saying, and then.
No, that was what I was kind of handing it over to you.
Okay, so that I've had it running for several months now, and put it in a cooler so it was more thermally stable, all this stuff, and I have convinced myself that article was complete bullshit.
This is the sort of foam that has conductive particles in it, and as it compresses, you get a different signal, and so is that you're doing something like that?
Yeah. So what it was you take the foam like ICs come on, and take some conductive glue a couple of 1-inch squares of single-sided copper-clad board to it, and basically make a resistor divider or whatever you want to do to measure change in resistance across it.
Wheatstone Bridge.
Yeah, and whatever you want. I think in the article, I think the guy had done the time to charge a capacitor through it.
Okay. RC curve.
Which is fine. Anyway, and he said, well, it's going to be dependent on temperature and humidity and, everything. Literally position of the moon.
Oh, yeah, okay. Yeah.
And yeah, so literally, this is one of those times where you can say alignment of the planets, and you're not joking. But
what is it? What are they trying to detect?
A gravitational tide.
Oh, okay. So
yeah,
like really,
really alignment of the planet, and so the author had.
Now we need the fairy with the wand to come in. Yeah.
Well, the author had showed this plot and said, okay, it's this diurnal-looking thing, and that's what I expect because gravitational tides are roughly diurnal depending on where you are in the cycle.
Wait a minute. I thought there were 6 hours, and that's why the tides are what they are now.
Well, so if you actually plot solid Earth tide, not ocean tide, because we don't care about ocean tide.
So we're not doing lunar tide strictly. We're doing Earth tide. Okay.
Well, you care about the actual gravitational force. You get period doubling because you got a bolt on each side of the Earth.
Right.
In the ocean, and that actually doesn't correspond with gravity change. So I wrote this program that does a model based on the canonical Longman paper that actually calculates what the gravitational tide is. What is gravity throughout the day? And I verified it with other models and convinced myself that this is 100% right. And initially, this sensor looked pretty good. They kind of lined up. But then if you watch it, if you watch it for months, they eventually just phase drift all over the place, and it very, very accurately measures temperature and humidity change.
So many sensors do.
And if you
you said something about the HVAC system in the building in your tweet about it.
Yeah, so if you correct for all of that, you get pretty much nothing.
Noise.
And what tipped me off is I put it in our building here. Well, other than cross-plotting it and seeing these huge lines, I put it in our building here, and I said, well, I'm going to try to get away from as much of that as I can. The author didn't do this, but I put it in a vacuum chamber and pulled a vacuum on it. And not a great vacuum, like 25 millimeters mercury. And
still, it's not going to be variable relative to the external atmosphere, right?
Right, and there's a small temperature change in the vacuum chamber just because...
Radiant coupling.
Radiant heat, yeah.
And
but
conductive.
So I plotted the data and I saw something that looked 24-hour period. I said, oh, cool. I plotted the model, and right now we expect actually a little period doubling. So it didn't line up. Okay, it doesn't look so great. Then I plot the temperature, or I plot like 8 a.m. and 6 p.m. on it, and it's very clearly our building's HVAC system kicking on in the morning, kicking off at night. So it doesn't look like it works. I was a little surprised that you could detect something that small with that crude of a sensor.
It's useful for something else.
Yeah,
It's
I mean,
not just that it doesn't work for what you want.
I've since done some calculations, and noticed the modulus of the foam was not even close to what it is. It wouldn't work. I've come up with a better design that might actually measure gravity, but this one's pretty much conclusively busted. I did figure out that if you put USB batteries in a vacuum chamber, nothing horrible would happen. I was a little concerned about the battery breaching and smoldering.
Yeah,
I thought the lithiums were usually vacuum packed to begin with.
I didn't know what the construction technology was, so I put it in and sat up there for a few hours and made sure that there was nothing suspicious going on before I took off. Because our engineering building, one of the labs, caught on fire a couple of weeks ago, so they're really skittish about that stuff right now.
You put lithium polymer into the vacuum?
It was I don't have an identical one here, but it was one
One
of
of
those.
those prismatic cells, right?
Yeah, it was like a phone charger, battery.
Yeah,
USB
those are
charger.
LiPo.
Yeah.
Man, I can't believe those survived.
I
can.
I didn't know if they would, but they
If
did.
you drop them too hard, they can combust.
Yeah.
But the nice thing is there's no oxygen in the vacuum chamber.
Yeah, I guess that's true.
Yeah,
They're not a
so
chemical fire. They're an oxygen fire.
Yeah, I
And
mean,
then-
after all, it's the lithium oxidizing that does the big issue. That becomes the big
Yeah.
issue there.
Yeah.
It
Which
did
is
survive.
also-
This is, I mean, it's super cool what you did. I mean, it's like good science happening. And then it's almost like you should publish or at least post somewhere what you've done.
Exactly.
Because it's people shouldn't believe this paper that was put out.
Well, so this was an article in Nuts and Bolts, and Nuts and Bolts sells the kit to build this thing.
Oh, for crying out loud.
Oh, no.
Well, that sucks.
And
That's a conflict of interest.
well, so I'm writing an article for Nuts and Bolts right now on something totally unrelated. And so next time I've got a meeting with the editor, we're supposed to talk about this. What do you do? Because I understand that you're making a little bit of money on the kit, and that's great, but you're selling this to kids, and they're thinking they're learning about gravitational tide, and they're really learning about HVAC schedules.
Well, just remark. That's just changing text on a web page. It's just like, hey kids, do you want to learn about HVAC systems?
You want to have a combined temperature and humidity sensor because those are usually combined anyway. So why not just go?
Something under constrained, not unique.
Want to see my LiPo battery?
I actually did have a question though. So the one I'm thinking of revising this, because I was going to give a talk at AGU, a 5-minute talk on cheap gravitational sensing, and basically my talk is now turned into this doesn't work. So
it's cool though.
I did a bunch of calculations and said, well, if you have like a weight on a spring and 2 plates and you make a capacitor out of it, and you depend on gravitational tide to move those plates closer or further apart, you get a really tiny capacitance change. It's not that great, and the temperature dependence on the length of your spring is going to swamp everything.
Wait a minute. What if you use like nitinol or something like that and use a charge amplifier?
Well, so what I was curious about is I've seen capacitive distance measurement units that can get really great resolution, like a few nanometers resolution.
Usually they're using a charge amplifier.
So yeah, what is there a relatively cheap one of those?
Well, it depends on what frequency range and what capacitance range you want to live in, but you could even use a 741 amplifier just configured as a charge amp to do that if you want as a single stage. The other possibility is that instead of using an air dielectric, you use some sort of piezoelectric or ferroelectric dielectric instead. Even Saran wrap will work for it, and that will give you a significantly higher capacitance and significantly higher capacitance drift. Like, for example, if you keep saran wrap at the same temperature and relatively the same humidity, but you have a mass on it, that should deform repeatably. And saran wrap itself is actually a really, really good dielectric, so you can probably get into the nanofarad range with that. So displacements being equivalent to several nanofarads, and that, well, actually, that could feed into like the RC portion of a 555, and then you can do frequency dependence, which is actually really similar to a circuit that Don's been working on for. He does it for resistance in water conductivity, but Don, what was the name of that thing again? The 555 based conductivity meter that you were working with?
So the output of it, of the 555, this frequency, we were connecting to a speaker because it was kind of an engaging way of assessing the signal. And someone happened to know that there was this really annoying frog in Puerto Rico that everybody hates called the coqui because it makes noise and keeps people up at night. And so they named it the coqui. That's what it's called.
Wow.
This was really annoying, the sound. Yeah. Anyway, yeah.
So the coqui is, in your case, it's a variable resistance rather than variable capacitance 555, but basically do the same thing. And your pitch variance on the output, or in this case, if you want to just keep it as frequency, record it in audio, and then just look at that frequency at some point in the future, then, I mean, the 555 does add another level of complexity insofar as deconvolving the temperature dependence out, but if you're inside, hopefully that wouldn't be as big of a problem.
It'd be pretty simple. I'll just say quickly that when we were interested in measuring depth, we instead, I mean, so the way that you tune the frequency on the 555 is you have a capacitor and a certain resistor in the circuit, and so for the conductivity, which is the sort of the inverse of the resistivity, we were fixing the capacitor and varying the resistance, and then we get the variable frequency out. But for depth, we actually fixed the resistor and attached a long extension cord and put that in the water, and then the amount of the extension cord that was covered in water, that different dielectric changes the overall capacitance of the wire, and so we got a different signal out of that. We didn't get to. I haven't really played with that a lot, but that's just to say that you just tweak the circuit a little bit, and then you've got a way of measuring the capacitance.
Yeah, I've seen stuff like that before. Like, gosh, it was a long time ago, but I came across a humidity sensor that was the application circuit they recommended was one of these like frequency capacitive.
Right.
Yeah, just what you described it basically. It was like a 555 timer circuit that was like. Had the sensor in circuit.
Yeah, it was doing it as a capacitance to frequency converter. Cool. So, John, I think that might work.
Yeah, that might work, and I think my others, I mean, real gravimeters, the $100,000 Centrex CG5s use this zero-length quartz spring and all this, but I think we can adopt from that. It probably should be ovenized.
That's a good point. But the other thing to consider is that it's also really easy to get your hands on piezoelectric ceramics nowadays, which can give you displacement differences on the order of, let's see, if I remember correctly, it's going to be on the order of nanofarads it's 10 nanofarads per, other way around, 0.1 nanofarads per micron. So if you have like a ball on the back of a piezo buzzer element, and then you have a really nice flat piece underneath there, and somehow you have the ball centered, then you should be able to detect tides with that, with either the 555 or a charge amplifier.
Okay.
How do you I don't understand how piezoelectric elements and capacitance have, like, what do you? I'm not sure. I thought piezoelectrics generate voltages.
They do if you're putting AC mechanical force into them. But if your alternating signal, so to speak, that you're picking up is extremely slow, if it's close to DC, then it's more that you're sensing the change in pressure on the element. Because a piezoelectric, when you're moving it quickly, it becomes essentially an energy harvesting device, and can also be a it can be a transducer when you're putting AC in electricity into it. But when you're working closer to the DC range, they turn instead into relatively high capacitance capacitors, where the capacitance can be varied by deformation. So since these are essentially ferroelectrics, meaning that once you put a field on them, they retain that field as long as the field is on there with very low loss in between. That's why they're so relatively high resistance. That's why piezoelectrics are usually in the single-digit to tens of gigaohm range for straight resistance, because they're essentially just a solid dielectric capacitor that will keep its entire crystalline polarization interior to itself as long as the field is applied. There's also remnant polarization and the hysteresis of repolarizing, and that's actually what causes part of the mechanical displacement, especially in PZT, which is lead zirconium titanate. You have this cubic zirconium titanate shell, and then you have several lead atoms that are in there, and those actually squeeze out of the middle of the crystalline structure and then squeeze back in. And so as you do this kind of oscillating squeezing, these higher atomic number masses in the form of those lead atoms actually cause these large changes in density. And so the density change on one particular axis within the ceramic or crystal, in the case of like PMNPT single crystals, that actually causes the strain that you see, that then adds to being able to do actuation. Similarly, if you compress it and then pull it back out, you're moving these leads around a lot very quickly, and so they are actually changing the electron cloud configuration of the zirconium titanate crystalline structure around them. And so by doing that, that's when you start actually seeing the charge difference occur across the polarized axis of the piezo. Yeah, sorry, this is the year that I spent at the materials research lab at Penn State talking here.
Okay,
so they're
wow.
they're kind of like magnetic generators. Yeah.
In essence, and that's why the term ferroelectric as opposed to ferromagnetic is usually applied to piezoelectrics. Because just like with a ferromagnetic thing that can acquire a magnetic charge, quote unquote, or spin really, by being exposed to a DC magnetic field, these acquire a DC electric field by being exposed to a DC electric field. And then they keep that remnant polarization across them for some amount of time, and then there's a degradation. But if you're working on the same order of time scale as you'd normally see for that sort of repolarization, rather than working in the AC range higher up where you don't have a depolarization, and that's going to increase the strain across the element, then when you're working in these lower frequency, longer period ranges, that's when you can actually see the change in capacitance itself rather than seeing change in electrical output from a galvanic sensor, if you will, something that's sourcing current. If you work slow enough, in other words, the loss tangent of the piezoelectric or the ferroelectric dielectric is too high and you lose too much charge through it for it to be outputting voltage. Basically, it's self-discharging at low frequencies. But at a low enough frequency, you can still measure the capacitance really easily, and the capacitance change is sufficiently large that at several what was I saying? Several hundreds of picofarads per micron of displacement or of strain. That's going to be something that you should be able to see pretty easily if you put like a piece of lead shot on top of it, on top of a flat piece of steel, and then put it into a 555. You should hear like an octave change over the course of 1 day, according to what you're saying. Depending, of course, on the size of the lead shot.
Right.
You know, the other thing, John, you're ultimately you're just trying to measure small distance, yeah? That's kind of the...
That's all I'm doing, yeah.
So, Pete, you know, I never actually used it, but I got samples of these linear, and it's linear distance you're trying to measure, right?
Yeah.
So, here, I got samples of these guys by just asking for them. They're a company that's like in Europe somewhere.
Were you thinking LVDTs?
No, it's a linear incremental position sensor, and I think it works based on a magnetic, like a specialized magnetic strip. So like it measures the distance.
Oh, one of those encoder ones. Okay.
Yeah, it's like a little. Here, I'll put a link in the
chat window.
Notes over here. Yeah, I think this is the one I got. John, it might be worth taking a look at.
I'm pulling it up here now.
You can only buy them in like thousands, but they'll send you a sample.
And also a survey. As soon as you bring it up.
So anyway, take a look at it.
It says that the minimum pole pair length is 4 millimeters.
4 millimeters. So what is the distance you're looking for, nanometers?
Yeah, I mean, it depends on how compliant of a spring you put on, because ultimately you're looking at force change over time, because acceleration's changing. But acceleration,
Delta G.
Gravitational acceleration changes are on the order of 0.1 milligauss, so you're like out in the 7th decimal place or something like that.
Holy crap.
And meters per second squared.
As well, because it's got a high spring constant itself, but as soon as you put a known mass on it, then it's compliant enough that it will deform. That's why they're made for acoustic transducers.
But even I don't know if this will work, and I'll have to run the numbers and see, because I've got all these calculations in a notebook at home. Even if it doesn't work, I think I'm going to try to get a sample, because this looks like a really fun transducer. I did think about LVDTs, and I actually have a couple sitting in a box up here that might be worth giving a shot.
There is one question that I'd have about the LVDT, though. Sorry.
Yeah. I was just going to say, like, I mean, when you're talking about distances that are that small, I mean, how do you... It just seems like the breeze or whatever would, would have a huge impact.
Yeah. No, I mean, I think that's why putting it in boxes and boxes and boxes, maybe ovenized, so there's no airflow.
Yeah.
And lots of averaging to get rid of any vibration.
Right. Okay.
That's a big deal. I mean, when we do the $100,000 gravimeters out in the field, you always think about like, oh well, it's windy and there's lots of trees around here, so got to stop work.
Right.
And
or even like you said, like, and I know you guys in the geology field are all about keeping the ground from shaking when you're trying to measure shaking ground, right?
Right.
So that's got to, I mean, a nanometer. God, if you take a wrong step, you got to isolate all that, right?
Well, the other thing that I was going to say about the LVDT is actually magnetic field dependence is going to play in.
Yeah, and I don't know, with LVDTs, I'm a little... I use them for some of my displacement measurements on earthquake experiments in the lab, and I'm actually seeing you get a little bit different magnetic heating of the core that's position dependent on where the core is inside the LVDT. So you actually, as you go from one end to the other, the LVDT, you get this kind of weird nonlinear drift looking thing in there.
It's kind of like an MRI field where it's a magnetic field gradient rather than one particular field.
Yeah, and that's a problem. That really is making me want to buy one of these laser distance sensors.
Do it.
I was just going to ask, like, is this is something that maybe people might take an optics approach to measuring tiny distance?
Yeah, I mean, these things are a few grand, but that's what grants are for, and since it would be used for something in the lab, and then repurpose it.
Right.
But even if you had like the optics, imagine. I mean, could you possibly get a zoomed in enough a microscope that would actually see that displacement happening?
Well, that's the thing. You get an optical distance sensor, and the whole thing's integrated into one. Or
Yeah, and these are
two pieces, really, because you got the retroreflector and the source measurement. It's essentially a Raman spectrometer head.
I mean,
Okay.
I think some of the ones I was looking at were they were interferometry-based stuff.
Mm.
But then again, I mean, thermal is still huge. Moving everything, changing the spring constant of your spring, it's a nightmare. It might be one of those things where I may have picked the wrong thing to try to demo a cheap sensor for.
Actually, there is one other thing that comes to mind, though, and that's actually the optical strip measurement methods that are used for DROs on mills and lathes. Because some of those are sub 10,000th of an inch, and it's going to be in the micron range.
Yeah, I don't think we're going to get microns of displacement, though.
No, that's true.
Why
Unless
doesn't-
you amplify this somehow.
So like are all sort of conventional accelerometers, even really expensive ones, just not sensitive enough to pick this stuff up?
Pretty
I'd say
much,
yes.
yeah. I mean,
Okay.
even the early gravimeters were still masses on zero-link springs that you very carefully balanced in these ovenized vacuum chambers.
Huh.
It's a tiny thing, so like I said, I may be picking the wrong thing to try to demo for people. I thought it'd be a cool idea, and then that article maybe said, oh, maybe this is doable, but no, it's not. At least not in the way that article
What
shows
about just using a light balance instead? I mean, that's the way that we've done it in the modern physics lab here at Cornell, is that we've got basically two lead masses with a mirror in between them, and those two are on long lengths of lever arm, and then in that case, I mean, you're doing gravitational attraction between two lead masses, which is actually even smaller than what the tidal force would be. But if you just change the axis, you should be able to do it that way.
But you need a really long projection surface to amplify a nanometers of displacement into something measurable on a wall or something.
The ones that we've got here, the path length is 10 feet. And it's two 2 kilogram lead balls.
So you're basically doing the Cavendish experiment, right? Like the torsional version? Yeah.
Yep.
Okay.
The nice thing there too is that you can sort of look into the actual like 1/r² at short distances and say something about string theory. I think that would be like a nice outcome.
Well,
Right.
I think even if we're just talking about the optics of it with regards to diffusion, and also if you have a sufficiently collimated laser pointed at it from far enough, even from very close, now you can sweep across an arc of a room. So if you're demoing in a gym, this is no problem. So,
Lots to think about. Yeah, lots to think about.
Between that and a time-lapse camera, you might actually be able to capture some tidal patterns.
That would be actually a really cool light painting project.
Yeah. Definitely.
Yeah, we'll have
Kind
to.
of reminds me of what we were getting up to, Don, at the workshop with the laser sweeps through the smoke on the campfire.
Yeah, that was super cool. Yeah.
We were sweeping a green laser pointer through while somebody had an SLR on really, really long exposure, and we were essentially able to do PIV by looking at the sweep of the laser and then looking at all of the vorticity in what we happened to illuminate. It was really cool.
That's cool. Yeah, that sounds cool.
Wow.
It wasn't even light painting per se, because it wasn't a long exposure. We were just like at daylight settings, and he would snap that, and the laser was bright enough that we were able to actually discern all the particles that were in the beam.
Neat.
It might even be worth, since we can predict the gravitational tide to ridiculous accuracy. Like what you actually measure from the really expensive gravimeters and what we actually hopefully would measure with this and the model all should line up. It could even be a cool light painting project just to take the model and run it in real time and project it with a laser on a wall.
That would be cool.
Because that would be relatively easy to do. I mean, I have the model.
I'm surprised though. So you're talking about the actual It's because it's all driven by like celestial mechanics, right?
It's all driven by, so all you have to do is program, a few hundred lines of really awful spherical trig.
Yeah. Okay.
And at least you've already done it, right?
Yeah. No, I've already done it, and it.
So now you have to hand wind the galvanometer.
Well,
that's the other boring part of this project.
Yeah. That's why there's Netflix.
Oh man, Friday nights.
Yeah.
That's how we get spent.
John, you sir are a masochist. I have to hand it to you.
Yeah.
Last time I wound a coil, it was on my wood lathe, and that didn't exactly turn out well. No pun intended.
Yeah. And well, I guess I think I have to take off.
So do I. But
yeah, that sounds about right.
But we should do this more often than not, because
Yes.
that way we don't have 3 hours of things to catch up on.
Right on.
And
all right.
Cool.
yeah.
Take care, guys.
Yeah,
Have a good
great
one.
to meet you guys.
All right. Yeah. Good to meet you. See ya.
See ya.
Bye.